Can everyone see well? I hope so. Just let me know if not. Okay. Hi, everyone. Thank you for the introduction and the invite to come here and present today. My name is Konstantin. I'm a PhD student in my last year at University of Warwick and NYU, and I'm gonna talk about geographically aware machine learning for neural networks today, and how I imagine that we can improve neural network models to be better at learning spatial patterns. So this talk's going to be a bit more, it's early in the morning, so it's not going to be crazy technical, and a bit also an overview on the landscape that is machine learning for geospatial data. So let's start at the very beginning. What are spatial models and why are they needed? If we revisit the very simple linear model that you probably all learned in undergraduate or so, one of the key assumptions for getting a good estimate that is a linear unbiased estimate is that the error term of our model, so this little epsilon back here, is uncorrelated. So it's iid independently and identically distributed. And this key assumption is, of course, not true for many cases in the real world, and that is because often, like a simple linear model struggles with omitted variables, or with is not able to account for systemic variation that underlies the data generation process. And the two most common causes here are spatial and temporal dependencies. So working with time series data or working with spatial data. In these cases, usually you'll have, when you run a simple linear regression or so, a linear model, you'll have an error term that is autocorrelated in space or time. This is obviously, that's a problem for economists and people who are interested in identification. But for machine learning, it should not necessarily be a problem, because we're not interested in identification, but in prediction. So the question is, why should we care about spatially dependent residuals? And the answer to that is quite simple, because having correlated residuals also means that you're omitting some information about the process you want to model that might be important for improving your model. So in short, if you account for systemic variation like spatial autocorrelated residuals, you might be able to get a better model, a more robust model, a more true to the real process model. And so a simple way of solving that is, for instance, just plugging in spatial features into our model. So for instance, if we have a linear regression model, plugging in the point coordinates of the observations we have. Now, of course, a linear model is not able to capture two-dimensional spatial patterns really well, but we'll come to that. Yes, so basically, the first question that comes to mind when we think about spatial dependencies and spatially correlated error terms is, how do we even identify that? How do we identify in a process that there is some spatial dependency? Because not every data that is actually geographic, for instance, must have a spatial autocorrelation. There are plenty of geospatial data sets that don't exhibit that spatial autocorrelation. So the first intuition we need is kind of metrics to measure spatial dependencies in data. And this is, well, I'll start to go a bit into methods and also in the history of how this has been done in the past. I don't have a watch here. Just let me quickly check how quick I am. All right. Okay. So yes, like I said, first we will dig into some spatial metrics for measuring spatial effects. And if you want to look into that, you will start with literature from a lot of different fields. So there's obviously the GIS community, has long thought about these questions, but there are also more applied fields that just encounter these problems so often in their research that they've also developed their very own methods for accounting for spatial effects. And that would be, for instance, ecology, which is very big in spatial statistics, but also fields like geology or atmospheric sciences. And most of these, to take already the kind of main point of my talk, is most of these have not really found their way into the machine learning community, as far as I can tell. And I think there's a great opportunity there to take ideas from all of these different fields, ideas that are aimed at resolving issues of spatial dependence and merging it with machine learning. Right, so let's start with maybe the most common metric of measuring spatial dependence in data, and that is the Moran's I metric that stems originally from a mathematician called Moran, who developed it in 1950 for n-dimensional space. So he worked in geometry and just wanted to find a measure that measures the dependence of data point on the global mean, like the spatial dependence, for n-dimensional space. And then in 1995, one of the great GIS researchers, Luc Anselin, conceptualized that very much aimed at the GIS community and for geospatial patterns. And Moran's I is a very useful tool for measuring spatial autocorrelation of model residuals, for instance. So it's often used when people try to see if their linear regression model has spatially autocorrelated residuals. And what it basically does is it measures the direction and degree of local spatial dependencies. And so just to also take that a bit forward now, is the Moran's I statistic is what I'm going to look a lot in this presentation, and I'm basically trying to merge this with existing machine learning methods. Moran's I has also been expanded in several ways to capture a little different spatial effects, and so I'm also going to quickly go over two of these extended extensions of Moran's I. The first one is a spatial heteroscedasticity. So instead of looking at the mean and comparing that to a global mean, for spatial heteroscedasticity, we look at the variance at each observation and see how that varies from the global mean variance. And this was developed more recently by also two very famous researchers in the GIS space, Ort and Gettis, who also have their very own spatial autocorrelation metric. And they developed that in 2012. And this measure is very useful for finding outliers in the variance compared to the global scale. And so as you can see already in the formulation, so basically the spatial heteroscedasticity Losch metric is just a simple extension of the Moran's I. And lastly, also just one more step from that is the very recent Lsd metric, which was developed by René Westerholt in 2018, and doesn't compare the local point variance with the global variance, but rather the local point variance with the neighborhood variance. So instead of always looking at the global variance, we look at the specifically defined neighborhood variance. So that is a much more smaller neighborhood level effect that we can observe with this, rather than just comparing it to the whole global variance. And the metric Lsd and Losch are very different and not correlated, as you can see on the figure on the right side. So the Lsd metric captures a very different process to Losch and also to Moran's I. And this is also from René Westerholt's paper. This is a very cool figure, I think, because it kind of shows how all of these metrics, Losch and Lsd metric capture very different things. And So as you can see, the Lsd metric is much more interested in finding local clusters, whereas the Lsd metric is much more looks much more into global change points. And yeah, so by the way, I can really recommend that paper. I have it in the references at the end of the presentation. It's a very interesting paper for thinking about spatial dependencies in data. Last thing maybe I can mention on all of these is, so all of these metrics are calculated using this little w, which is a sparse weight matrix. And this weight matrix can take all sorts of forms and works with discrete and continuous data. For discrete data, you might want to, like you can think about this like an image where you take, for each pixel, you take the exact neighbor bordering images. And for point data, you can think about the weights as probably taken or obtained from a nearest neighbor approach. But basically, this weight matrix is a parameter, and but allows for very flexible computation of these metrics. All right. So having introduced some metrics of measuring spatial dependence, traditional metrics that come from outside of the machine learning community, my question is, how do we learn spatial patterns in current machine learning? This is kind of the second bit. This is now the machine learning bit that I want to talk about. So traditionally, machine learning, of course, has ways of dealing with spatially autocorrelated data, and I want to briefly introduce the current kind of state of the art, or the methods that are currently used for accounting for that. The first and probably most important model are, of course, Gaussian processes, which are kernel-based method, and of course, kernels are very, very much able to account for neighborhoods, because they learn a kernel around each data point that kind of captures these local effects. Gaussian processes have some issues because they traditionally scale poorly to high dimensional data domains. Recently, there's been some good progress on this, though, with the deep Gaussian processes, especially the gPyTorch package on Python I can really recommend, and further techniques like kernel interpolation that try to simplify the computation. Another issue that GPs have is that they're traditionally constricted by Euclidean distances. So the kernels usually only basically take the direct distance between points. There's been some work on graph kernels that allow for non-Euclidean distance and even asymmetric distances between points, but this is still very much in the works, and not, well, as far as I can tell, the progress is not hasn't been a breakthrough there yet. For neural networks, the classic approach for accounting for local spatial dependencies are, of course, convolutions and convolutional neural nets, where a bunch of pixels are analyzed together. Basically, I'm sure you all know what convolutions are. The traditional problem of CNNs is, of course, that they only work on image data, on discrete data. However, also recently, there's been a big boom in graph neural networks that allow for modeling of all sorts of continuous data structures. Another issue with convolutions is that they traditionally are more looking into local patterns, but that's also recently been solved, I guess, to say, for lack of a better word, by attention mechanisms who allow for learning all sorts of local and global patterns simultaneously. So having kind of talked about the two main, well, it's not even models, it's model families that are used for analyzing spatial data, I'm coming a bit closer to what I'm interested in doing, which is combining these ideas from GIS, these kind of metrics that measure very, very particular spatial effects, and combining them with these existing machine learning methods, especially neural networks. I'm not really looking into Gaussian processes here, but yeah. And there is in my book kind of three subfields to think about. The first one would be spatial conditioning, auxiliary information, and embeddings. The second one would be spatial model selection. And the last one, which is my research, would be spatially explicit learning. So integrating spatial constraints in the loss functions. But let's start with spatial conditioning and auxiliary information. Just a quick time check. All right. I'll hop through these a bit quicker, I think. So with spatially conditioned models, I mean just models that are always dependent on the spatial context. And with spatial embeddings, I mean ways of compressing spatial information or learning embeddings or latent representations in the training process. And two papers I want to point out in that sense that I really like is first the conditional density estimation Gaussian process from NeurIPS 2018. It's work from colleagues at Imperial College, and this work really neatly shows that if you combine GPs with latent variables, you can get really good at estimating spatially dependent distributions. And what's particularly cool about this is it works in low-dimensional space too, because it's a Bayesian model. The second paper, which I'm also sure lots of you will know, is Tile2Vec, which is an embeddings paper that borrows of the word-to-vec approach, vector embeddings approach for geographic image data, so satellite image data. And I thought it's a very neat paper, and it's a cool way of learning representations unsupervised for very, very complex remote sensing data. Oh yeah, the last paper was very recent from ICLA this year, which I also really recommend to all of you. It's a bit more complex than. Oh, I'm sorry for the noise. There's some construction in my house. Yeah. This last paper I wanna point out is Base2Vec from ICLA this year, and that's a very exciting paper, I think, because the motivation for this work comes from actual spatial perception in the brain. And so it borrows heavily from neuroscience, where it has been found that humans encode spatial information using sinusoid functions in the brain. And the authors borrow from that approach to build a very, very neat spatial embedding. I've worked with that a little bit, and I can recommend that it works quite well as a kind of general geospatial point embedding. Oh, and it's also another cool thing. It's independent of scale. Can work with varying scales and also multiple scales at the same time. The second thing I want to talk about, the spatial model selection. This is going to be a bit more brief because there's not super much work on this, but there's one rather old paper from the ecology community on the spatial AIC, so the archaic information criterion, which is a very common metric of doing model selection, not so much in neural networks, but in tree-based models and so on. And the authors have proposed a spatially explicit version of that metric to overcome suboptimal selection in the presence of spatial autocorrelation. And lastly, for the spatial model selection, so this is the first of my papers that I'm just going to touch on this briefly and then talk about another paper, but this is a paper by me and some co-authors from UCL and DeepMind, which is on GANs and how GANs can be helped to learn spatial data better by leveraging the Morin's I metric that we've talked about before as a model selection tool. So here we have trained GANs to generate point patterns and use the Morin's I metric as a selection tool for these GANs. The second thing that we did in this paper is that we also had a conditional conditioning in the GAN that conditioned each data point on the features of its neighbors. So you also had kind of that explicit spatial conditioning in there, and then a spatial model selection through the Morin's I. All right, so having touched on these a bit, this is the point, or this is the theme that I want to talk about the most in this presentation. That is kind of what I call spatially explicit learning. It's a bit I don't know, I still have to think about how I'm going to call it in my thesis, because I think I might make some people angry, because obviously GPs are already spatially explicit if you want to think about it like that. But maybe I'll call it more geographically explicit loss functions and geographically explicit learning, because I borrowed these metrics from the geography community. So this is my most recent paper with my collaborator Daniel at NYU. And the question that we basically want to ask ourselves as a follow-up from the SpaceGAN paper is, where we used Moran's I for model selection, is, can we also use it for explicit learning? Can we use it in the loss function? Yeah, so the question is, can explicit learning of spatial autoregressive embeddings like the Moran's I improve the performance of neural network models? And in a nutshell, what we do is we first propose a new version of the Moran's I that is multi-resolution. It's very simple. It just, I'll have a figure on that later on. So that's yeah, a simple expansion of the Moran's I to make it work at multiple resolutions. We integrate that multi-resolution embedding as an auxiliary task in the training process, where we try to predict that spatial embedding at the same time as we try to predict our main task. And this approach is very simple and modular and compatible with all sorts of neural network models. And I'll show that on generative and predictive tasks. Right, so first thing is the multi-resolution local Moran's I that we have developed. So if you think about the original Moran's I, it's kind of you have an input spatial pattern, and as an output you have spatial autocorrelation values for each of the data points. So the output is the exact same shape as the input. Yes. Did I miss something here? No, I think that's described well. And the kind of multi-resolution approach we propose is that we downsample through average pooling. We downsample our images to kind of an arbitrary amount. In this case, we do it twice, right? So we downsample the image twice, and then for each of the downsampled images, we again compute the local Moran's I, and then upsample the whole image again to the original size using nearest neighbor interpolation, so that it retains the kind of coarseness of the structure. And that way, we hope to capture the local spatial autocorrelation at different levels. And ideally, we hope that embedding this in the training process can improve our learning process. Now, the issue with auxiliary task learning is basically, how do you find a weight in your loss function for the auxiliary task loss? Most papers that you will find out there actually hard code that in. So they probably do some trial and error studies and then have a hard weight. We also do that in our approach, and it works too, but it's a bit of a mess to find the ideal weight. So a pretty neat approach is the following by Alex Kendall and Yarin Gal, so the Bayesian deep learning people, Oxford and Cambridge. In 2018, they proposed to weigh the tasks in multitask learning by their uncertainty. So they originally proposed it for a multitask learning approach, which auxiliary task learning is too, but for auxiliary task learning, the difference is that we're only interested in performance metrics on the main task. So this paper provides a very simple, very neat approach to automatically learn these weights on the fly. And that is exactly what we do. All right, so let's talk about some experiments that we did. So this paper is not completely finished. So that's why this are, I guess, somewhat work in progress results, but we can pretty much say that it works pretty well. And we want to show that in two experiments. The first one being spatial interpolation. So imagine you have a 32 to 32 pixels input image, and you just want to zoom in and get to a 64 to 64 resolution. And If you do that and include the Moran's IA auxiliary task, that seems to work quite well. So we tried this both with a hard auxiliary task weight, and here what I present in these GIFs is with uncertainty weights that are learned on the fly. Note that here we only use the single resolution Moran's I. We don't use the multi-resolution Moran's I in this particular model. But basically, our results show that we outperform the kind of vanilla CNN version that we use to predict that. If you plug in our auxiliary task, it performs better. And here you can see the results a little bit. So on the very left, you have the real to be predicted image, and then all sorts of benchmarks. So bicubic interpolation, inverse distance weighting, ordinary kriging, universal kriging, and then a simple CNN and a CNN with our improved auxiliary task method. And the orange boxes are supposed to highlight a bit the parts where it's visually, where it's visible that our model makes things a bit better. It's hard to tell, but the performance it's not massive. It's rather small, but it's significant. All right, the second and last experiment is generative modeling. So basically, can we learn the generative data generation process of a spatial pattern with those auxiliary tasks better? And to do that, we use GANs as a generator. And yeah, this figure shows a bit the kind of single resolution Moran's I and the multi-resolution Moran's I auxiliary tasks, and how they're plugged into the GAN. And this is done by putting them in so the generator remains untouched. The generator generates fake data. For that fake data, we compute the multi-resolution or single resolution Moran's I, and we do the same thing for the real data. And then all of these are plugged together in the discriminator, and the discriminator then has multiple tasks where the discriminator learns to predict whether the real image is real or fake, and also whether the embedding of the image is real or fake. I'm jumping a bit through that, but if you have questions on the kind of particularities of GANs, you can ask me that later. So we try out our approach with all sorts of GAN architectures. We use the original vanilla GAN. We use a deep convolutional GAN. We use a deep convolutional GAN with Wasserstein loss. And we also use a GAN that actually comes from the GIS community. So there was a pretty cool paper in, I think, International Journal of Geographic Information Science on an encoder-decoder GAN for spatial interpolation. So I also recommend that paper. It should be in my references as well. And so we use all of these, and for each of these, we can just plug in our auxiliary task again and see how it works. And these are just some sample results. So the data we use here is tree canopy data from Canada. So basically, the pixel values indicate how thick the tree covering is at this point, and we are able to generate pretty realistic data using our approach. The evaluation for the GANs is a bit more tricky. We also show that there are performance increases from our approach over the vanilla versions of each model, but that's a bit harder to show for us. I have some results here where we do that. So the first data set on the left is a toy data set that basically is like a Gaussian peak and the Gaussian dip that always appear mirrored from one another. And our approach seems to do better on this, not by much, but a bit. And then on the right side, the data is underwater, or what's it called, relief data. So basically it's a map of an underwater region. And for this, it's a bit less clear to see that our model is performing better, and it's also very close. But this is also the part of the paper we're still working on, is kind of improving our model a little bit more so that the gap to the vanilla versions get a bit more clear. All right, I'm pretty much done, and I think exactly half an hour. So I just want to close with some ideas and brainstorming on the future of research in that I want to go. And the first thing is, of course, different real-world cases of complex spatial patterns and applications that might benefit from this, or that might be worth exploring. Then I'm of course wondering about different spatial metrics. For instance, would this kind of same approach work with a Lush metric and the Lsd metrics I've talked about before? I have not yet tried that, but it's very simple to plug in, and that's definitely something that I'm planning for the future. And you know, what are other metrics that I haven't thought about yet that might be worthwhile exploring in this sense? And then, of course, that's a gun-related point, is how can we measure the fidelity of synthetic spatial data? So if you know a bit about GANs, then you know that the computer vision community is very particular scores for GANs that are Cauchy inception distance or something like that, that are aimed at kind of proving how realistic a fake image is. And these methods are not necessarily applicable to GANs. So are there maybe ways of designing metrics that are aimed at geospatial data? And then also since I know that there's a bunch of people from the AR4EO lab here that might be interested in knowing what else I'm working on, I just quickly wanted to list other projects I'm working on to let you know that if you're interested in collaborating or work on something similar, please feel free to reach out. So I'm also working on differentially private point patterns. So basically using GANs with a point net, so point transformer module to generate, for instance, what we used is 311 call data from New York. So you have like your urban point pattern, and is there a way to learn that point pattern in a differentially private way so that you can then release synthetic data that is true to the data generating process while preserving privacy for the data points. I also work on informal settlement population estimation. There's a big project on that at the University of Warwick, and we only did some preliminary work on this with Google AI and Accra, but we hope to continue that. And then lastly, I am also working on expanding this whole spatial metric focused learning into the spatial temporal domain, and here focusing on designing new spatial temporal autoregressive embeddings, and then maybe also plugging them in a similar way to what I did with the SXL paper into spatial temporal learning. And with that, thanks for listening. Thanks for stopping by so early in the morning. I'm happy to share this presentation if I can somehow. Maybe you can let me know about this, but here is the references and the papers I've been talking about. So yes, thank you very much.
Thank you very much, Konstantin, for your presentation. Now I open the round for questions. Any comments? Okay, I have a first question. While you were presenting your experiment number 2, you used an auxiliary value, a lambda, to weight the tasks. So how did you set it? And what's, let's say, the impact of that value?
Yeah. So the thing with this figure is that it still shows the kind of old way of how we did it. So that's the kind of first draft of the paper is where we used a lambda value to weigh the auxiliary tasks. We have gotten rid of this. Well, we didn't get rid of this completely, but this is replaced by uncertainty weights here. The formulation of the uncertainty weights you can find in the Yaringal paper. But I can briefly go through how we did it originally. So originally we had one lambda value for all the auxiliary tasks. So every auxiliary task was weighted the same way. And originally we went through this by trial and error. So we tested different values out and checked how the model works. This is actually quite common in the multitask learning community, that you look a bit for the parameter by just testing it out. And we found that the lambda value of 0.1 works best, 0.1. And that's still true. It actually is still, in some cases, the hard weight for the auxiliary task is still the best way to do it. It's better than the uncertainty weights in some cases.
Thanks.
Can you maybe also say something about, so this is how you did it originally, but now how does it work exactly with the uncertainty? Just the intuition, maybe that would be great.
Yeah, I was thinking about including that up, kind of the maths, but I thought it was too much for the whole presentation.
Yeah, I think that the math would have been definitely too much. I'm just looking for the idea if that's feasible. We can also discuss it another time if it's too much for the moment.
Right. Let me go back to the slide I had on this. Yeah. So the idea here is that so basically for each of the tasks, you can kind of compute the uncertainty, the noise of how noisy is that task to a learner. And based on that, you can compute a weight that gives like a more noisy task, a more complicated task, a lower weight, and that weight can be adapted into summed up into a multitask loss, and then added together. And these weights can in that way can be learned on the fly. And the Python implementation is super simple. It's actually in our SpaceNet repo, so you can just look it up. It's very simple. But that's the idea behind it.
Are there more questions? Please feel free to write them down on the chat or ask them.
So, Konstantin, thanks a lot for your interesting talk. I have one comment to your last slide regarding how to validate the fidelity of synthetic data. I just want to say that in our lab, we have Patrick Eber, who is not here today, but he is working on basically cloud removal from radar and optical data. And he has built up a data set consisting of more than 100,000 triplets of cloudy optical data and clean optical data taken in a very close time, and radar correspondence, which is more describing the spatial context, exactly what you are looking at, the textures. So maybe this could be interesting data sets for you, because after you generate the image, you can basically compare to rather realistic optical data taken at the same place.
That would be very interesting. Yeah, I think that's a good idea. So like so far I haven't worked with satellite imagery, but I know that actually for satellite imagery that is generated by GANs, people use the classic metrics. They use FID, inception score. But I wonder if there might be an avenue for actually developing something new that is more aimed at this kind of particular imagery. And just also briefly to say what we used in our approach, we used MMD, so maximum marginal discrepancy, and we used what was the other? Oh yeah, the classifier two-sample test. So that's basically training a simple nearest neighbor classifier to distinguish real from fake images, and the score from that classifier is then your fidelity score on images. But thanks for the tip.
Yeah, but I just think on the one hand, probably one could explore the spatial metrics you're introducing, because at the moment, the whole system is trained in a cycle-GAN style. And yeah.
Very cool.
On the one hand, he can probably benefit from your approach. On the other hand, maybe his datasets could be an interesting datasets for you. I don't know.
Okay, thank you. Any other questions?
Okay, so again, thank you very much Konstantin, for your talk. It was very interesting, and hopefully we will have it online very soon. Thank you very much, all of you, for attending this, and I hope to see you in the future.
Thank you very much for coming by.
Thanks, Konstantin.